In this video, we're going to continue looking at the process of finding eigenvalues and eigenvectors of these linear operators. And in this case, let's just jump right into an example that we're going to take a look at. So let's see, here's our transformation. And let's look at an operator that acts on R3, right? So three-dimensional vectors turn into other three-dimensional vectors. And then here is what our operator does. So I'm going to just write down our standard matrix. In this case, let's use like 5, 2, -1, 0, 3, 4, 0, 0, -2, and then that's times our v. All right. Now, if you notice, I chose a 3 by 3 upper triangular matrix, and it was done for a reason. And towards the end of the video, I'll kind of highlight a couple key things here. But in general, there are formulas, for instance, for the characteristic polynomial for higher dimensional operators, but it's not as simple as the one that we derived for the 2 by 2. So let's just go back to first principles to come up with the characteristic equation for this particular transformation. All right, so remember it's a minus lambda I. So in this case, our I is going to be the 3 by 3 identity. So in this case, it's going to be, here's our A, 5, 2, -1, 0, 3, 4, 0, 0, -2, and then minus lambda times 1, 0, 0, 0, 1, 0, 0, 0, 1. And what is true, regardless of the dimension of our operator, when you do your a minus lambda I, all you end up doing is subtracting lambda from the elements on the main diagonal. So I'm going to have 5 minus lambda, 2, -1, and then 0, 3 minus lambda, 4, and then 0, 0, -2 minus lambda, right? So that's our well, that's the start of finding the characteristic polynomial, but then we have to find the determinant of this. So the determinant, which is what we call our p of lambda, so the determinant of a minus lambda I. Now you might remember that when you have a triangular matrix, it's very easy to compute the determinant. It's simply the product of the entries on the main diagonal. So you'll have 5 minus lambda, and then 3 minus lambda, and then -2 minus lambda. And look at that. It is a polynomial. It's a polynomial of third degree, but it's in factored form, which we love, because now if we set our polynomial equal to 0 to find its roots, we're basically finding the root of each of the factors. So we can see that lambda 1 is going to be equal to 5. Lambda 2, and I mean, there's no particular order here, right? Our lambda 2 is going to be 3, and then our lambda 3 is going to be -2. And again, I just want to point something out here. Again, we're basically just focusing on the process again, but look at these 3 eigenvalues that we just came up with. And then look at the entries on the main diagonal of our original standard matrix for a transformation. They're identical, right? And it's not a coincidence, which is another reason why we love our triangular matrices. They make things so much easier, right? So we have our eigenvalues. Now we have to find the eigenvectors for each of these eigenvalues. And no matter how easy it is to find the eigenvalues, finding the eigenvectors, we always have to go back to our homogeneous system. So in this case, I'm going to start with lambda 1. The homogeneous system, what are we going to do? We're going to subtract 5 from the entries on the main diagonal and then augment it with our column of 0. So if I do that, I'll have 0, 2, -1, and then 0, -2, 4, and then 0, 0, -7, and then that is augmented, right, with our column of zeros, right? So that's what it looks like when lambda is equal to 5. But that's kind of interesting because we don't really see this, or we haven't seen this a lot, but look, in our first column, there is no pivot, right? We have pivots in the other two columns, but we don't have any pivot in the first column. So what does that mean? It means that our x1 is actually our free variable, right? So our x1 is our free variable. And probably we don't want it to be equal to 0. We kind of saw that pattern in the previous cases. But then if you look at, for instance, the third equation, it tells us that x3 has to be equal to 0. And then look at the second equation. If x3 is equal to 0, then it tells us that x2 has to be equal to 0, right? So we don't even really, in many instances, right, it's really important to be able to interpret what the homogeneous system is, right? If you wanted to go through and do the formal RREF, feel free to do that, but the key is going to be making sure that you identify where your free variables are. So here is the eigenvector, or all the eigenvectors that are associated with the lambda of 5. So the first component can be any real number except 0, and then but the other two components have to be equal to 0. And then of course, if we wanted to identify a basis for this eigenspace, then we can just factor out that t, and then here is the eigenpair. Right, so our eigenpair, in this case, lambda is 5, and then here's a basis for all of them, right? And again, remember what this means is that if you take any scalar multiple of the vector 1, 0, 0, and multiply it by this matrix or transform it using this operator, the result is always going to be 5 times as long as the original vector acting in the same direction, right? Okay, so and then we just kind of rinse and repeat. We do that for lambda equals 3, so now our second eigenvalue. And again, remember what we're going to do is we're going to subtract 3 from the elements on the main diagonal, so let's do that. We're going to have 2, 2, negative 1, and then 0, 0, 4, and then 0, 0, so negative 5, right? And then we'll have 0, 0, 0. All right, so what does this tell us? Well, for sure, x3 is going to be equal to 0. That's for sure. There is no pivot in the second column, right? Because the 2 is not a pivot. It's not our leading entry. So x2 is going to be our free variable, not equal to 0, presumably. And then we should be able to solve for x1. So let's see. So we have x1 plus 2t. I'll just write, I guess we could do minus 0. We don't really have to. And then subtract 2t from both sides. So x1 is negative 2t. All right, so here's our second eigenvector, so v2. So we will have negative 2t there, and then t for our free variable, and then but our third component has to be equal to 0. So if we take out a t, then we're left with this as a basis. So negative 2, 1, 0, and then our eigenpair is 3, and then our basis is negative 2, 1, 0. All right, and then finally, when lambda is equal to negative 2, so negative 2, so now we're subtracting negative 2, which means we're adding 2 to the entries on our main diagonal. So we will have 7, 2, negative 1, Then we'll have 0, 5, 4, and then 0, 0, 0, right? And then now, so no pivot in column 3, so our x3 is going to be our free variable. Again, presumably not equal to 0. And then now we can do our sort of back substitution. And notice I'm not even doing any, I'm not doing much elimination at all, right? We just have to know how to interpret our system. So 5x2 is equal to negative 4t, just moving that term over. So that means x2 is negative 4/5 t. And then take all of this, put it in the top equation. So you'll have 7x1 plus 2 times this. So that actually is just going to make it negative 8/5. So 8/5 t, and then minus t, and then that's equal to 0. And we just have to solve this. So this will give us a negative 13/5 t, move that over. So you'll have 7x1 is 13/5 t, and then divide both sides by 7. So x1 is 13 over 35t. All right, so then here's our third eigenvector. So it's any vector of the form 13 over 25t, and then negative 4 over 5t, and then t, and then we can take out our t, and then here's our basis, right? So all non-zero scalar multiples of this, 13 over 25 minus 4 over 5, and then 1. Now, if you didn't want all these fractions, what we could do is we could multiply everything by 25, and I'll write that down as our eigenpair. So the eigenpair, when for lambda negative 2, here is a vector with only integer entries. So you'll have 13, 25 times negative 4/5 is negative 20, and then 25 times the 1 gives us 25, and then that could be our basis, right? So again, the process isn't that much difficult, or this one didn't work out to be super tedious because we had a nice upper triangular matrix. But I just want to point out that if our matrix is not of a special form and the dimension is getting greater and greater, so like 4 by 4, 5 by 5, and it's not triangular or any nice pattern, the algebra becomes tedious almost to the point where you'd end up having to use software to even find the roots of the polynomial, because the degree of that polynomial is just going to keep getting higher. The solving the homogeneous system, though, doesn't really get any more difficult. It's just that your eigenvalues might not be nice integer or even fractional values like we've been seeing, right? But there you go. So the process works, right? But with a lot of things in algebra, when things scale, the complexity increases just in terms of how tedious the process might be. So next up, we're going to look at some more general properties, and we're going to state some of the properties that we've kind of observed right here in this example as it relates to triangular matrices. So hopefully you're interested, and we'll see you then.